So PyLith step 10.cfg. And first let's look at that'll run. But first, here's step 10 on the screen. So I have static simulation, total time equals 0. I give it a dt of 5. This helps non-dimensionalize the slip rates that show up in our internal solve for the fault friction. Boundary conditions I'm going to do on x positive, x negative, and the bottom. So these most of these 3D hex 8, we're putting boundary conditions displacements on the two x normal faces, and then roller boundary conditions on the bottom. We have one fault. Here we've switched the solver to being the solver nonlinear. And so here I'm specifying, up till now we've often used zero displacement boundary conditions. Here I'm using a simple database for the boundary conditions. It's called fixed displacement axial shear. I'm constraining the x and y degrees of freedom on the positive faces, z on the bottom. So let's look at what those. So this spatial database, here's what the x degree of freedom is. So displacement in x direction is -1 meters times x divided by 3 kilometers. So at -3 kilometers, my x displacement is 1. Positive 3 kilometers, my x displacement is -1. So on the negative side, I'm pushing in. On the positive side, I'm bringing the boundary closer together. That's to put some normal stress on the fault. And then the shear, at -3, I go 1 meter in the lateral direction. On the other end, I go 1 meter of lateral displacement on the other direction. And so here I'm giving the boundaries, these displacement boundary conditions are at the two boundaries, and by having this linear variation, the values on one boundary will be set to the values on the first row. The values on the other boundary will be put on the second row. I could have put these on different spatial databases, but I chose to just stick them all in one spatial database. So for the faults, I'm giving a zero tolerance here of 10 to the -9. I changed from the fault cohesive kinematic, the default, to fault cohesive dynamic. Again, node set label for the fault, static friction, quadrature, Fiat Lagrange. This is 3D hex 8. So for hexes and quads, we use Lagrange quadrature. And basis functions. The friction properties, uniform database with a coefficient friction of 0.6, zero cohesion. Here are my PETSI settings. For that inner friction solve, I'm going to use additive Schwartz. Don't need many iterations, so I say cut off at 25. If you want to, I commented out the information that it would show on the screen for those friction solves. You can turn those on if you'd like. We're going to do VTK output. So there are the VTK settings. I'll show you the PyLith app.file. Let's look at our solver tolerances. So in this case, the relative are absolute. Interesting. So why didn't our fault isn't slipping, but here I did not put any additional SNES settings, so I guess I can get away with. But you'll notice here we have a relative tolerance of 10 to the -10, absolute tolerance of 10 to the -20, and 10 to the -10 and -9. Not our suggested settings, but when I look back over here and you can see our run, if I scroll up, you'll see that we did a SNES iteration, came down, the fault remained locked, And I can tell that because we did not need any nonlinear iterations. Our second SNES evaluation gave us 10 to the minus 13, indicating it converged due to absolute tolerance. So let's look at what this simulation produced. Oops. So now we have to sift through all of our files. So here's our box. Let's distort it by a factor of 1,000. So we'll see, boop, well, maybe not 1,000, 500. But you'll notice we've squeezed the box. If I put on the original in a wireframe mode, whoops. So there was our undeformed configuration. So we've squeezed the box and then we've sheared the box. And I'll show you the wireframe. Let's do displacement in the Y direction and surface with edges. So here was our fault, through-going fault, and you'll notice that continuous displacement across the fault corresponding to zero slip. So we have sheared the box, but we did not overcome static friction. So the fault has remained locked. And if we look at, go down to step 10, look at the fault output. So there's the fault output. And I can use the calculator and I can calculate the along strike traction, divide that by the normal traction. And so here you can see that in the middle, and I should really do minus because compression is negative. So you'll notice that so the biggest value is about 0.38. I have a coefficient of friction of 0.6. And so I'm well under what tractions would cause fault slip in this case. Any questions about this case where the fault didn't slip? Okay, well let's move on then the case where it does slip. So step 11. So let's see. Pretty much it's going to be another static simulation, same boundary conditions, except now instead of having 1 meter of displacement, we're up to 3 meters of lateral displacement. So we squeeze it again, move each side in by 1 meter, but then laterally we move the boundaries 3 meters. Static frictions, coefficient of friction of 0.6, zero cohesion. Again, no change in our PETZ parameters. So let's run step 11. You'll notice now you can see it going through a nonlinear solve. So it's going through, in this case, this is a through-going fault. And our little approximation of updating how much slip is required to adjust the Lagrange multipliers does not work very well when we have a through-going fault. If the fault is isolated in the middle domain, it actually works much better. But with our new formulation, we can overcome that. So here we are. It took 51 nonlinear iterations. You can see here was our inner friction solve. They was converging in 5 iterations, converged to absolute tolerance. So I believe in this case we do have, yes, we do have turned on error if not converged. SNES error if not converged. So the fact that we ran all the way through is an indication that the solution never diverged in either the linear or nonlinear solves through that entire 51 iterations. So let's look at the results. So load up step 3 in the faults. No, not step 3. Step 11. So there's our faults. We'll do slip. So we have on the edges, it's about 0.9 meters of slip. In the middle, it's 1.8. And the reason why we don't have uniform slip is our tractions are not uniform. Oh, that's the magnitude of tractions. So our normal tractions, because we have free surfaces at the boundaries of the box, remember we grabbed the box and basically sheared it where the y boundaries are free surfaces. This creates that when we shear it, just move parallel displacements in these free surfaces, the normal stresses at those ends, as you can see here, is less than the normal stress is in the middle. So that creates a difference in traction. Here is the traction, so bigger tractions in the middle than at the edges corresponding to these normal stresses. And if we use our calculator here and compute traction x minus, sorry, I want to do minus traction x divided by traction z. You'll notice now, other than the corners, we are at a value of 0.6 consistent with our coefficient of friction. So we have a little bit of sort of small perturbations associated with sort of corner effects and discretization errors at the edges. And let's look at the displacement. So we know we slipped, but we don't know what the displacement field looks like. So let's, oops. Here's the 3D box, turn off that. Let's warp it by a factor of 200. And so there you can see, let's color displacement in the y direction. There you can see the offset in the faults. It goes all the way through our box. And so let's turn on surface with edges. There you can see the offset across the fault. There's a little on the bottom. We have no vertical displacement on anywhere except we can't pin the fault. Remember, we can't constrain the degrees of freedom right at the fault. So we constrain everywhere else on the bottom. And so we get a little bit of edge effects where there's a little bit of uplift. The fact that these corners, the reason why the coefficient of the ratio of the shear stress in the long strike direction was not divided by the normal stress was not 0.6 is there's some shear stress in the vertical direction. So the shear stress in the plane divided by the normal stress is equal to 0.6 at those locations. Any questions about this example? Okay, let's do one more where we're going to do a quasi-static where we'll start out with the boundaries and slowly move the boundaries until they start to move or until the fault starts to fail. And let's see. So step 13, quasi-static slip weakening with stick slip behavior. So the fault will slip. It'll go down to a lower dynamic value. And so then the fault will lock. When the fault locks, then the coefficient of friction will reset to the static value, allowing us to build up more stress until it overcomes the static coefficient of friction again. The fault friction will drop. We'll get more slip. and then the process will repeat itself. So let's look at the input file for step 13. Very much sort of the same overall conditions. Total time now, we're going to do 200 years with a 5-year time step. And for the fault, we're going to start out with on the face x positive, we're going to hold initially it fixed, and we'll move it inward 1 meter and then hold it fixed, but then drive it with a uniform slip rate or displacement rate of 1 centimeter per year. So initially we're going to move the boundary in, and then we're going to slide it at 1 centimeter per year parallel to the fault. On the Y face, there's no initial displacement, and so what's going to happen is we'll move one boundary in 1 meter, and then we'll start to shear, and one boundary will move in one direction 1 centimeter per year, the other boundary parallel will move 1 centimeter in the opposite direction. And on the bottom, outside of the faults, we'll constrain the vertical degrees of freedom. Now our slip model is slip weakening friction, and then we want to force the healing once the sliding has stopped. So this is a flag to turn on the force healing equals to true, so that the fault will reset itself once it's slipped at the dynamic value. It'll reset itself. And so what it's doing if you look at our fault constitutive model, so here's our slip weakening friction. As we accumulate slip, PyLith is keeping track of slip at each point in the vector sense. So if you slip 1 meter this way and then say make a 90-degree turn and start slipping 1 meter the other direction, it'll say, well, I slipped 1 meter plus 1 meter in the other direction for a total of 2 meters. It's not doing sort of where you started from. It's keeping track of the distance you slipped along the slip path. So basically it's integrating along the path how much it slipped. So that's what this D, remember this is just a scalar for the coefficient of friction. So as the slip accumulates along the path, it's integrating the distance along that path. It is comparing that to D0 to get down from the static coefficient down to the dynamic coefficient of friction. Now once at a time step it's locked back up, it resets the accumulated distance along the slip path. So the fault builds up friction, it slides, it stops, then the force healing resets this cumulative slip distance back to 0, so it'll start reaccumulating slip up here from the static value, decreasing down to the dynamic value. So this is how you get stick-slip behavior in a quasi-static simulation. Same friction model parameters. Here's our coefficient of static friction is 0.6. Dynamic friction relatively high at 0.5. Slip weakening parameter of 0.2 meters. So we're going to transition from 0.6 to 0.5 as we accumulate 0.2 meters of slip and a cohesion of 0. So that's all here in our uniform spatial database. Here's our PETSI settings. Let's see, still pretty much the same PETSI settings. So let's run step 13. So here we're running multiple time steps of the nonlinear solve, so it's going to take a little while to run, because at each time step it's going to do a nonlinear solve that involves a number of iterations. When the fault is stuck, it jumps through those time steps very quickly because the nonlinear solve will converge in one iteration. Whereas when it's slipping, the nonlinear solve takes more iterations. So that's one of the things you'll see as these residual norms are sliding by. Sometimes you'll see it's doing just a bunch of linear solves, and it's going back to a nonlinear solve. So it's actually spending most of the time doing the nonlinear solves. So it's the slipping time steps with slip, where the solver is spending most of its time. Any questions while this is running? How does it?
How does PyLith track? How does PyLith calculate? Okay, what is log now?
So PyLith at each time step, that initial solve, it assumes it's locked, and then it looks, and when it does that first nonlinear iteration, we solve for the Lagrange multipliers. And the Lagrange multipliers are telling us what the tractions are on the fault. If the Lagrange multipliers, so we have both the slip, we can compute the slip based on the displacement field, and then we also have the Lagrange multipliers with the traction. So we compare the Lagrange multipliers to the friction tractions that we get for the fault constitutive model for that given amount of slip, which in that case is usually that means it's 0 because we're stuck. If the tractions are greater than the Lagrange multipliers are greater than the tractions allowed by friction, that means we need to allow the fault to slip, and so we compute an estimate of how much slip we need to reduce the fault tractions. You can think of slip as reducing or relieving the stress on the fault, and so we slip it a little bit. And look, did we slip it enough or slip it too much based on what the fault tractions are for that amount of slip, and then adjust things accordingly, and then repeat that process until we satisfy that the Lagrange multipliers are equal to those allowed by the friction model within a given tolerance. So this ran, so let's look at the results. So we are in step 13. So here, this is an example of VTK files with multiple time steps. So here we have a bunch of time steps. And so what I do to load them all simultaneously, in the XMF files, HDF5 files, you just load them all up in a single file. Here they're in different files. Within ParaView, you just, instead of doing the cascade and selecting all of them, you just select them when they have the little double dot there. That selects things up, and you'll notice up here I have 0 of 11, so I'm going to have 11 time steps here. And so here's my fault. Let's color the y displacement, and let's warp it by a factor of 500. So I will step through these. Let's see, oops. Oh, I want to look down Z. There we go. So this is going to involve a lot of rescaling. Let's do the surface. So we haven't slipped yet. Haven't slipped. Building up a lot of stress there. We slipped once. Slipped some more. Building up more stress. Slipped. And that's where it ended. We didn't write out that much information. The ground surface, we output more time steps. So let's do step 3, the ground surface. Let's also add in step 13 on the fault. Step 13, fault. So, whoops, gotta go 3D mode, Rescale. So there we have the ground surface. We'll do the ground surface edges, displacement in the y direction. We'll see where we are at the end and rescale it. So in the end, we have a total of 2 meters of offset. So we start at the beginning for the fault. Let's show this. Let's show the tractions. Let's show the shear tractions. So another thing to point out is that the tractions that we write out in the output files are a long strike shear traction, then the up dip shear traction, and then the fault normal traction. So even though it says X, Y, and Z, they are not in the global X, Y, Z coordinate frame. They're in the local fault X, Y, Z coordinate frame. So here's our tractions on the fault surface, and we'll have displacements. So now we'll step through. Let's see. So we're building up stress on the fault. Oh, I need to warp the ground surface. I'm not seeing the slip. Let's warp it. What did we have before? Let's do 400. Let's do 500. So we'll start over from the beginning again so you can see a little better. Build up of stress. Slip. And so I need to rescale my tractions here. Build up stress, slip, build up stress, slip. So you can see the stress is building up in the middle and then the slip. So if I start this over, build up stress, and you can see that sort of flashing. Increase in stress, stress drops. Increase in stress as we deform, and then the stress drops. So that's sort of stick-slip behavior in a little box with a through-going fault. We created earthquakes. Any questions on this one? Okay, I'll go through one more example. And this will be, we'll switch the gears a bit and